Okay, this is lesson 2.4, simplifying rational expressions. First, we're going to look at some examples of what a rational expression is. And basically, it's a quotient, meaning fraction, of polynomials. And we looked at what a polynomial is earlier in the unit. So we just need to make sure that we have a fraction with a polynomial on top and bottom. So our first example is 1 over x. This is the simple rational expression. 1 is a polynomial, and so is x. And we have a fraction. So we have a quotient of two polynomials. Similarly, x squared, polynomial, that's a quadratic, over x squared minus 6, another quadratic, polynomial over polynomial. We're good to go. In our third example, we have an x term, we have a 2 term, and we have a minus 3 over x. And we could turn this into one big fraction, but as it's written right now, we have just one term with a fraction, and it's a polynomial over a polynomial. So this is a rational expression because we have a fraction of two polynomials. Some non-examples. Root x over x squared minus 1. X squared minus 1 is a quadratic, so that's a polynomial, but the square root of x is not a polynomial. So we have a fraction, but we don't have two polynomials. Similar to this fraction, top's a polynomial, bottom isn't, because in a polynomial expression you can't have a fractional exponent. Same with this expression, we have another fractional exponent, and we don't have a fraction at all in terms of a quotient of two polynomials. So what we're going to do in this lesson is we're going to simplify these rational expressions. And what that means is it's kind of like reducing a fraction. You're looking for ways that you can divide factors out of the top and bottom. So say we had a fraction like 2 over 4. We know we could simplify that fraction to 1 over 2. They're similar fractions, and 1 over 2 is the reduced form of that fraction. The reason why we can reduce it is because 2 is common to both the top and bottom. So let me write that out for a second here. We have 2 over 4 as a fraction, and we can say that it's equal to 1 over 2. And the reason why is because, well, the 2 over 4 is just 2 times 1 over 2 times 2. And we can divide the 2's away, and we end up with 1 over 2. So we're dividing away a common factor. That's what reducing a fraction is. So we're going to apply that to a rational expression. When you're simplifying a rational expression, you have to state the restrictions. And what a restriction is it accounts for any value of x or any variable that could cause the denominator, the bottom of the fraction, to be equal to 0. Because we know we can't divide by 0, and any x value that would make you have to divide by 0 is stated as a restriction. And we'll look at that after we reduce our fractions or our rational expressions. So let's do two examples. In the first example, I've got it already fully factored. And that's actually the first step of simplifying a rational expression, is to simplify it down to its factors so you can see what you can reduce. And I lied to you just now, it's not fully factored. It looks like it is because we have two pairs of brackets on top and bottom, but the bottom bracket has a common factor in the first bracket. That common factor is 2. So we should factor fully. Everything else is going to stay the same, but I am going to common factor that 2 out. And the reason I'm doing that is because we want to fully factor and then look to see if there's any like terms on top and bottom. And now we can look. Just like when we simplified that fraction 2 over 4, we can look for any common factors. And on the top we have an x minus 1 term, and on the bottom we also have an x minus 1 term. So those terms can be divided away, and this is reducing the fraction or simplifying the rational expression. Now the top only has the 3x minus 5 term, and the bottom has the 2 and the 2x plus 1. So we fully factored, and then we divided away any like factors. What makes these questions challenging is the factoring usually. Once you've got it factored, it's quite easy to see which ones are the same and divide them away. The second tricky part is stating the restrictions. So I'm going to show you what I mean by that. We got some space down here at the bottom, so I'm going to use the space at the bottom. We go back, and after we fully factored, we look at each of the factors. So we have 3 on the bottom. We have 2, x minus 1, and 2x plus 1. Any factor that has an x in it can lead to a restriction. So our first bracket, x minus 1, there is a value of x that if I were to put it in, I would get 0 in this bracket. And if I had 0 in this bracket, 0 times 2 is still 0, and 0 times this bracket, whatever's in there, is still 0, which would make the whole bottom of the fraction 0, and we can't have that. So we know that we can't have this x minus 1 factor equal 0. So we can say that x minus 1 can't be 0. And if we simplify this by isolating for x, add 1 to both sides, we get that x can't be 1. And that's a restriction. Because if we put 1 in for x, this bracket is 0, and then the whole denominator is 0. There's a second restriction, and it's right here. 2x plus 1 also can't be 0. And if we start isolating for x, bring the 1 over, we get negative 1. Divide both sides by 2. X can't be negative a half. Now, you might be wondering, but we divided this one away, and it's not there anymore. So why is it a restriction? Well, the reason why it's a restriction is because it's a restriction on the original function. And dividing it away does simplify the expression, but the restriction doesn't leave. The restriction is still there. X still can't be 1. And there'll be a feature on the graph of this function because of that restriction. And that's more of an extension on the course, and actually I do an example of it in 2.5, completely optional. You can try it on your own, and by creating two graphs you can kind of see the difference between a restriction that divides away, this x equals negative 1, or x can't be 1, and a restriction that stays, 2x plus 1, or this x equals negative a half. They look different on the graph. There's two different types of behaviors on the function. Now, if this was the original function, and we didn't simplify it, this restriction wouldn't exist. It would only be this restriction. Okay? But a restriction that divides away does still count. So if it's in the original, it's part of the answer. It's part of the restriction. And where you list it is at the end. This is our simplified expression. We write comma, x can't equal, and then we do those fancy brackets for set notation, 1 and negative a half. Now, I probably should have listed those in order, but it doesn't matter. We're okay. All right, that's simplifying a rational expression. Now, what if it's not factored on top and bottom? Well, if it's not factored, you factor the top and bottom. So in the interest of saving some time, I'm going to say factor. And you can do that off to the side. You can do that on scrap paper. If you do it on scrap paper, though, include it with your answer, just because it is part of the answer. But we still want to work down from our expression, so it would kind of have to be off to the side. Now, I'm not going to actually do the factoring, because we did a lot of practice with factoring before the break and after the break. So I'm just going to factor it really quickly here and write it out factored. 3x minus 5 and 3x plus 4. It would be the factors for the top. There was a common factor there of negative 2. Always look for that common factor first. No common factor on the bottom, so we must have 3x minus 5. And it got to be a 3x again, plus 2. There we go. Fully factored on top and bottom. Okay, and both of these were complex trinomials, so you'd have to use decomposition to factor it. I would go practice on it off to the side. Make sure you can come up with those factors. And then once you've factored it, you're just looking for any terms that are equivalent, and you can divide them away. And we have a pair here. Now, what if we didn't have a pair? Well, if we didn't have a pair, that would be a fully simplified rational, and there wouldn't be any extra work that we could do. We would just have to state restrictions. And on the bottom, we're just left with 3x plus 2. Now, factoring fully to divide away and simplify, that's simplifying a rational expression. But if there's nothing to simplify, you still have to factor, because you can't find the restrictions, or it's quite complicated to find the restrictions from something that's not factored. Okay, so we need to factor even if it's just to state restrictions. Okay. So, what are the restrictions? Well, there's two terms on the bottom, so I'm going to write them down here. 3x minus 5 can't be 0, So if we start isolating, we get 3x can't equal 5, and if we divide both sides by 3, we get x can't be 5 over 3. And our second expression in the bottom is 3x plus 2. It also can't equal 0. So subtract 2 from both sides and divide both sides by 3. I didn't show the dividing step the last time. Oh well. We end up with negative 2 over 3. And there's our two restrictions. Now they're not answers, those are restrictions. The answer to this question is this simplified expression with the restrictions listed. X can't be negative 2 over 3 and 5 over 3. And that's it for simplifying expressions. Try the factoring, make sure you can end up with those factors, and then we'll do some practice in class tomorrow. Thanks for watching, and I'll see you next time.